Hello everyone, welcome to this online course on material science. I believe this is lecture 12 in the module 1 on magnetism. If you recall, in the last lecture we derived an expression for the atomic diamagnetic Hamiltonian, right? So let me write the expression to start this lecture. So we have some Hamiltonian, which is the diamagnetic Hamiltonian, and it's an operator, right? And from the previous lectures, we know Hamiltonian denotes the energy of a system. So in a way, this operator is the energy operator for a diamagnetic atom, right? And the atom has a closed shell electronic structure, right? That you know from the previous lectures. And the expression we found for this Hamiltonian goes like the electronic charge square divided by 8 times the mass of the electron. We need to sum over all the electrons, let's say from 1 to the z number of electrons. Then the magnitude of the vector product between the magnetic field and the position vector of the ith electron, right? And squared. So that's the diamagnetic Hamiltonian. We need to simplify this expression a bit more. So let's progress with this part of the expression, right? So what is this expression? B cross product with the position vector Ri, right? So we know this could be found out with the determinant. Ijk is the standard unit vector along x, y, and z, and then our magnetic field is pointing along z direction. So that's 0, 0, b, and the position vector for the ith atom is xi hat, yi hat, and zi hat, right? And let's evaluate the components of this vector. So for I, we have minus yi hat times b, and for j, minus is the convention we know. For j, let's see, so this is another minus xi times the vector magnitude of the magnetic field, right? So this turns out to be the ith component is minus yi times b, then plus the jth component is xi vector operator the position operator along x, this is position operator along y, times the magnetic field strength, right? And we need to find out the modulus square of this vector, so which is just the square of these components, right? So if we want to understand the value of this vector modulus square, we need to square this component, so which is b square, then yi operator square plus b square xi square, which is an operator, right? Just to make it more explicit, so this is xi square times the yi square, right? It makes sense. Now let's put this value on this expression. So the diamagnetic Hamiltonian now becomes, let me write it explicitly. So we have E squared by 8m, and then there is a B square, which is the magnitude square. So this will go out of the sum. So we can write E squared B square divided by 8m, and then we need to sum over all the electrons, the quantity xi square plus yi square, right? And both of them are position operators of the ith electron. So that's our expression for diamagnetic Hamiltonian written in explicit form. Now you have an operator, right? If you recall in previous lectures, I mentioned that once you have an operator, this represents some energy of the system for sure, right? But in this form, it doesn't have any value because you need to say what is the state of your system, right? And we are discussing a diamagnetic atom in a closed shell electronic structure. In that case, let us assume that the system is in the ground state. It means the atom is in its ground state, right? The minimum energy configuration, where all the electrons are moving in such a way that the energy of the system is minimized, right? So we have some ground state, right? So we have some ground state, and usually I have said that we denote this ground state by a ket vector, because it's a state of the system, it has to be a ket vector, and the fact that this is a ground state is denoted by putting a 0 here, right? So that's our ground state, right? So corresponding to this ground state, we know we have a corresponding bra ground state, which is 0 pointing this way, right? So now we have these two quantities, one, the operator itself, and the state. And I have mentioned many times before in the other lectures that once you have the state and the operator, now it is time to ask the question, what is the expected value, right? You remember this important term. And I told you that this expected value gives you the operator's magnitude or the value, right? For example, and you know how to calculate this expectation value given you know the state and the operator. The idea is that for the expectation value of this Hamiltonian, right? And this is an energy operator. So let us assume that once we calculate the expected value, it will give us the energy of the diamagnetic atom, right? That's our assumption. And this is nothing but the expectation value, and we know how to denote the expectation value, right? Putting an angular bracket in the both sides. Now this quantity means you need to form a integral, right? You remember that. So on the left you need the bra, and in the middle you will put the operator, and then on the right you put the operator, right? So the ket vector. That's how you perform the expectation value of the diamagnetic Hamiltonian. And once you calculate this value, right, you will get the energy of the system, okay? And we will calculate it soon enough. Let's try to calculate the value of this diamagnetic expectation value of this diamagnetic Hamiltonian. So all we need to do, we need to put the value of the diamagnetic expression from here, right? So let's do that. So we are calculating the expected value of the diamagnetic Hamiltonian, right? That's our goal. So first let's put the expression correctly. So we have E square B square divided by 8 times the mass of the electron. Then we have the sum over xi dot square plus yi square, right? Let me check whether I have the right expression here. Yes. So now we need to calculate this expectation value. You can see these are not operators, so these are just some numbers, so this will go out, right? The way, this is the first time we are performing any quantum mechanical calculation, so let me be more explicit. So this entire quantity goes out, then we are left with this bit, right? And we know we put this bit in between the bra and the ket because these are operators, so we cannot bring them out. They will operate on these states, right? So that's how we write the expression. So, and if you remember, what is this quantity, right? This quantity is nothing but, let's say, the expectation value just split into two, right, where you have xi square and then the other part where you have sum over yi square, right? Now it is same whether you perform the sum and then find out the expectation value, or find out the expectation value first and then the sum, right? It's the same thing. So the sum and the expectation value kind of commutes this operation. So you can write the term like I and then 0 times xi square plus, think about this expression for a moment. This is the first time I think you're seeing this expression. So you are calculating the expectation value first and then you are summing up. And here you are summing up first and then calculating the expectation value. These operations commute with each other. So we can write it in this form. Now the question is that what is this quantity, right? Do you know what is this quantity? You remember from one of the discussion I have had that for a spherical charge distribution, right, we know that x square plus yi square, right? If I remember correctly, this is nothing but 2/3 of the radius of the sphere that we are considering for the spherical charge distribution, right? This is 2/3 r square. You remember this expression, you can review the lecture. So what that means is that we can put r square or ri square more correctly in terms of these two, because this is nothing but the expectation value of what? The xi square, right? And this is nothing but expectation value of the y square in the ground state, right? In the ground state of the electron. So you add them up and this is nothing but 2/3 of the ri square for a spherical charge distribution, right? So we can put this value 2/3 there and we have E square by B square and then 8m. So let me be explicit, E square B square by 8m, and we are summing over still I, but we need to put 2/3 of the ri square here, right? And this 2 makes a 4 and 3 times 4 is 12. So we have the final expression for the expectation value is E square B square by 12m. We need to sum over this. Okay, that's our expression for the energy. That's E dia, expectation value of the energy. Nice. The next question is what to do with this value, right? Now the idea is that the magnetization of this atom or an ion, right? So it doesn't matter, maybe an ion or some atom. The condition is that we have a closed shell structure. Now the magnetization is defined by change of the energy of the system, which is E dia in this problem, divided by the change in the magnetic field. So the magnetization is defined as the change of your system energy due to the applied magnetic field. That's how we define the magnetization of an atom or an ion, right? Now if you look at this expression, minus is convention, so we have d dB and then the whole expression here, right, which is E square B square twice m, and we need to sum over the expectation value, right, of this quantity ri square. We need to sum over. And if you look at in this expression, everything is independent of b except the b square, right? So if you differentiate b square, you will get 2b, right? And that 2 will divide this 12 to 6, right? So the final expression, once you differentiate the expression, is e square, minus will be there, then b by 6m, and then the expectation value of this quantity, right, Ri square, and we are summing over this. This is an important expression. Now, the next step, we know that this is the magnetization for an atom or an ion. Let us assume that in this problem or in this material, let's say, we have n number of ions, right, per unit volume. So if you are asked to calculate the magnetization of that material per unit volume, you need to multiply the magnetization into per atom times n times v, right? So if you multiply e square b by 6m and then this expectation value, which is Ri, right, and the sum, this is the magnetization due to n such atoms per unit volume, right? And now we know how to define the susceptibility of that material, right? So if you recall that, I will explain this graph a bit later. If you recall, the susceptibility is defined by m by h, right? M is the magnetization per unit volume, which is this quantity, right? So let's write the expression for m, which is n by v. We have a minus sign, and then e square 6m, we have b, right? And then the expectation value summed over. Right? And so we have an h and b here. We know what is b by h, that's mu naught, the free space permeability, right? So we can change this expression to n times v and then mu naught, right? And e squared by 6m stays like this, and the sum, right? Now this is the susceptibility. We have the minus sign here, which represents the negative susceptibility of diamagnetism. Now let me tell you one thing, right? If you look in this graph, like this experimental data, they are plotting something known as the ZEF. I have mentioned in one of the previous lectures that I will explain at some point. Let me explain it now, right? So the idea goes something like this, that to fit this data with the expression, it is as though, let us say, we are considering some ion, right, or some atom, it doesn't matter, as long as we have a closed shell structure, right? For that ion or atom, right, we have said there are z electrons in that system, right? But we can think of this total number of electrons is divided by two parts, which is a part which is the effective and the other part is known as the core electron. It turns out that the core electron usually do not contribute to diamagnetism, right? Some of the electrons really which are in the outermost shell. So these are the core electrons, these are the electrons in the outermost shell. So the quantity of interest is the outermost shell electrons contribution, right? That's why this part usually is ignored, the core electrons. So we need the Z effective, right? And let us assume that all the electrons, right? We have some electrons in the outer shell, and we are assuming all the electrons that we have in the atoms in the, let's say, the outer shell has roughly a size of, say, like the expectation value of some Re square, right? So it means that if you have Z effective number of electrons inside your atom in the outermost shell, and you're summing over all the electrons here, right? So then we can think of in our model, right, we can think of that the sum of the size of all the electrons in the outermost shell is as though this quantity, right? And just be more pedantic and putting all the symbols, but you will not see these things in the books because they assume you understand already. So this is our assumption, right? So every electron in the outermost shell has roughly a size of this, right? And then we have ZeF number of electrons, the total size, which is this one, right? You're summing over all the sizes of the electrons. So this quantity represents the total area of the electrons around the outermost shell of the atom, right? So that's why instead of this expression, you can set up this expression, right? Then the susceptibility expression, you can write it as, you can see we have these factors, right? Minus n times v, then we have E squared by 6m, these are known quantity, right? So we have mu naught here again, mu naught, and then in terms of the expectation value, we write ZEF R square, right? And if you look at this graph, there actually this is our quantity, which is expectation value of an electron in the outermost shell, and right, and this is the number of electron in the outermost shell, right? And if you look at this expression, the susceptibility in the magnitude, if you forget the sign, the magnitude is scaling up with this quantity, right? And you can see the same here is true. So when ZEF is increasing, the susceptibility in magnitude is scaling up, right? For different ions, the size of ions are getting bigger, right? So this is consistent with the data. And usually if you look in the standard textbook, right, sometimes people quote this value of the diamagnetism in a molar system, right? So then for one mole object, you need to replace the number of ions by the Avogadro constant, right? The volume. So you need to understand how many atoms you have in one mole. That's like the Avogadro's number. So when you replace n by n, Na in this expression, this will give you the molar susceptibility, right? And then we have the expectation value of R square here. And usually, and all these values are known, right? You know the charge, the mass, the Na, everything is known to you. Sometimes you will see in the literature, they also convert this expression into something like this. So they would write E square by 6m mu naught Z effective, and in this expectation value, so this is some square distance expression, right? So they put the Bohr radius square to make it a unitless quantity, right? And then we need also an A square outside, right? So this A square cancels this A square, right? Now you know the Bohr radius, right, of an hydrogen atom. The standard value you can find. You know ZEF, you know mu naught, you know E square. Everything in this circle is known to you, right? And if you put those values, you will see the final expression usually written as the molar, right? Because we are using the Avogadro's number of ions. Molar diamagnetic susceptibility, you are putting all those values which is known to you. It will give you 0.79 Z effective, and then R by A naught square. And the idea is that this quantity usually tabulated for different ions. So you know these values of R square by A naught square. You know what is Z effective. You can easily estimate your dielectric susceptibility and measure and compare it with your experimental data, right? So this is the final expression for diamagnetic susceptibility of an piece of material where we have atoms in a closed shell structure, right, using quantum mechanics. And I think this is the end of discussion on diamagnetic behavior of the atoms. And then from the next lecture, I will try to explain how to tackle paramagnetic behavior in an atom. But for that, we need some more concept from quantum mechanics, right? So I told you this is a Kanban approach I am taking. I have told you most of the things, or all of the things that you need to know in quantum mechanics to understand this diamagnetic behavior, right? Now, you will see in the lectures to come, I will explain some more things from the framework of the quantum mechanics to understand paramagnetism, right? So this is the approach I was talking about. So I think that's about it, and the reference for this lecture is still the same, the 3 ones from Stephen Blundell, one from the Simon from Oxford University, and then the classic one, Ashcroft and Marmin, right? And I think that's about it, and thanks for listening.